So acid-base strength, we talked about this as a chemical equilibrium. Not all acids donate protons the same amount. So a strong acid, you do get 100% dissociation. You start out, before you dissolve it in the water, it's all HA, and in water it disassociates until you have essentially no HA. What you have is almost entirely A minus, the conjugate base of that acid, and H3O plus. So the extent of the dissociation is nearly 100% for a strong acid. If you think about equilibrium constants, you can never have all of one product, because then you'd have like an equilibrium constant that was infinity. It's never something infinity, it's just very large or very small if you're looking at the reverse reaction. For a weak acid, you get some partial dissociation. And so you have mostly HA. For most weak acids, it's mostly HA, but it has some dissociation. You get some production of H3O plus and the conjugate base pair. So a weak acid only partially dissociates. And a very weak acid essentially has no dissociation. You can see very minute amounts of H3O plus and A minus, but there's just not very much. So for a very weak acid, if you look at these equilibria, it's pushed far more towards the reactant side. And even a weak acid has sort of more of the ion, more of the species usually on the reactant side than the product side. Okay. So those are the different types of acid you can find. And if you have enough weak acid, you can still provide a lot of hydronium ions. It's just you won't get nearly as many per unit of molecule that you put in the water. So when we're looking at the extent of acid-base reactions and equilibria, when we're looking at strength of acids, it's really about a competition for the H+. So nitric acid is quite a strong acid. And in this case, when it reacts with H2O, then you get almost entirely nitrate ion, NO3 minus, and creation of a lot of hydronium. And so here, HNO3 plus, nitric acid is the stronger acid, and H2O is the stronger base because nitric acid can get hydronium to take all of its hydrogens, leaving only nitrate. So it must be the stronger acid. It's stronger at giving up that proton. The weaker acid wants the hydrogen more. So in this case, H3O plus, that's the weaker acid. It wants the hydrogen more than the nitrate does. It's weaker at donating H+. So we think about a weak acid, it means that it's weak at donating H+. The weaker base wants the hydrogen less, right? NO3 minus, it's a weaker base because it doesn't really want that hydrogen at all. It's weaker at accepting H+, it doesn't want it. The same way goes the stronger. The stronger, the stronger acid wants the hydrogen less. A really strong acid wants nothing to do with the hydrogen, it wants to give it away as fast as it can. And then a base, a stronger base would want the hydrogen more. H2O in this reaction is a stronger base than NO3 minus, the nitrate, because the stronger base wants the hydrogen more, it wants it more, and so we end up with more H3O plus because H2O wanted the hydrogen more than NO3 minus. And so when you're looking at acid-base reactions, you want to figure out, when you look at it, what direction will the reaction principally go? So looking at hydrochloric acid plus water, clearly the reaction is going to primarily go in that direction. If we look at something that's a weak acid, like hydrogen fluoride plus H2O reacting with to make hydronium ion and fluoride ion, it turns out that in this case, hydrogen fluoride is not a very strong acid. And so the reaction mostly is going the reverse direction. We start out with fluoride and hydronium, it will mostly go in the other direction and not create that much. And if you put hydrogen fluoride in water, it won't create that much hydronium. So that's what we're generally looking at, whether it's strong acid or not, what direction the reaction goes. Now, one thing that you've noticed is that in virtually all these reactions reacting with water. So water, whether it's a base or an acid. So water is interesting. It's called amphoteric because it can be either an acid or a base. Let's take a look of water reacting with some acid, HA. So in this case, H2O acts as a base. It accepts the proton from HA to create hydronium, plus, in this case, just A minus as the base. But in the case of ammonia, so then with ammonia, then H2O acts as an acid, right? Because it's a proton donor to ammonia in order to create hydroxide and a hydronium ion. So molecules that can both accept a hydrogen and donate a hydrogen are amphoteric, and water is by far the most common example. So looking at relative strengths of acids and conjugate bases, so you could really, if you're looking at strengths of acid, you could really consider something a strong acid if it wants to get rid of its H even more than hydronium does. You know, hydronium is a moderately strong acid. There's a lot of conditions whenever it's reacting with something like hydrogen fluoride, whenever it's reacting with a weak acid, it's willing to it can get that to accept its hydrogen. So that's sort of actually the definition of a strong acid. If it's a stronger acid than hydronium, then it's a strong acid, and it essentially entirely disassociates in water. If it's a less strong acid than H3O plus, then we call it a weak acid. So there are not that many strong acids, you know, probably of the relatively chemically simple ones. Those are most of them right there. You can always take an, you know, in some cases a strong acid and add a bunch of extra chemical functionality on one end. So those would sort of all fall under the same classification there, but there's far more weak acids. There's just, you know, a small list of really strong acids that are strong, that they give up their hydrogens more than hydronium. And then of course it goes the other direction at all. The stronger the acid is, the weaker the base is. If you look at the conjugate bases, here we got perchlorate, which is the conjugate base of perchloric acid. It's not a very strong base because it doesn't want H plus very much, right? Because hydrochloric acid is desperate to get rid of that HH plus, so the conjugate base is simply not going to accept it very much. So if we look down here, the conjugate bases actually increase in this direction. So you get down to something like OH minus, which is a pretty strong base because it likes to take an H plus to make water. So that's just an overview of some of the conjugate acids and bases and how they relate to each other.